In the previous video, we calculated the electric field magnitude along the symmetry axis of a uniformly charged ring. Then we established that this electric field should reach a maximum value for some finite distance from the center of the ring. In this video, we're going to compute that special location and then find the maximum strength of the electric field. So as a quick review, this ring has a total charge Q and radius R, and we calculated the electric field at a distance of x from the center of the ring along the symmetry axis. And that electric field turned out to be Q times x over 4 pi epsilon 0 times the quantity x squared plus r squared, all raised to the 3/2 power. And I'll post a link at the top to the previous video where this was derived. Now, after obtaining this solution, we looked at the small x limit and the large x limit for the electric field. And what we discovered is that the electric field is 0 at the center of the ring, and then provided that x is much less than r, in other words, the small x limit, the electric field grows linearly with x. So we see in the formula that provided x is very small, E is going to be proportional to x itself. Then when x becomes large compared to the size of the ring, in other words, x is much bigger than the ring's radius, the formula for the electric field reduces to the field of a point charge. And this makes sense because the ring will appear to be a point with charge Q if we move far enough away from it. This also means the electric field decreases asymptotically to 0 in the large x limit. So taking these two limits into consideration, E growing linearly from 0 at first, and then leveling off asymptotically to 0 in the large x limit, there must be some finite value of x for which the electric field reaches its maximum value. And we're going to call that value of x sub max. So how do we go about finding x max and the corresponding maximum electric field? Well, this is a classic optimization problem that we can solve by using differential calculus. And the idea there is that we see the slope of the electric field function is 0 at that maximum point. In other words, there's a horizontal tangent line there. So we're going to solve this by taking the x derivative of the electric field and then setting it equal to 0, and we should be able to solve for x max. So here's our electric field function, and we're trying to find the maximum value of this. And the first thing I want to point out is that the constants out in front don't matter for trying to optimize this function. So that's Q over 4 pi epsilon 0. And I'm going to say that our E of x is proportional to just the parts that matter. That's x in the numerator and x squared plus r squared to the 3/2 in the denominator. So to take the first derivative, we're going to have to use the quotient rule here. So we get the derivative of the numerator, that's just 1, multiplied by the denominator left alone. And that's an x squared plus r squared to the 3/2. And then we subtract from that the numerator times the derivative of the denominator. And we need the chain rule for this. So we're going to bring down that power of 3/2. We're just applying the power rule to this expression. So we have 3/2 times x squared plus r squared to the 1/2, subtracting 1 from the exponent there. And then we have to multiply by the derivative of that interior function, and that's a 2x. Now this whole thing is divided by the square of the original denominator. And that gives us an x squared plus r squared cubed. And we start to clean things up. We can cancel a factor of 2 in the second half of that numerator. And we can factor an x squared plus r squared to the 1/2 out of the numerator. This leaves us with an x squared plus r squared minus a 3 times x, or 3x squared. And we're still dividing by x squared plus r squared, all raised to the 3rd power. We can simplify the factors of x squared plus r squared in the numerator and denominator. And this leaves us with an x squared plus r squared to the 5/2 in the denominator. And then in the numerator, we have an x squared plus r squared minus 3x squared. So that'll simplify to r squared minus 2x squared. And again, the whole point with this approach to an optimization problem is that we're looking for the location of a horizontal tangent line. In other words, the location where the derivative is equal to 0. So we're setting this equal to 0 and trying to figure out what x is. The denominator isn't relevant to this calculation. I just need to know when the numerator is 0. So we get r squared minus 2x squared is equal to 0. Solving for the x squared, I have x squared is equal to r squared over 2. Taking the square root, we find our value of x max, and that's r over the square root of 2. Note that we aren't concerned with a negative square root here because we're talking about x as a distance from the center of the ring, so that's an inherently positive quantity. So now that we found this value of x where the electric field is maximum, We want to take X max and plug it back into the formula for electric field to find the maximum value of the electric field's magnitude. In other words, we're computing E of X max. So replacing X in this numerator with R over square root of 2, we get Q R over square root of 2 divided by 4 pi epsilon 0. And then we have an X squared. That's going to give us R squared over 2 plus R squared to the 3 halves. And now it's just a matter of cleaning up the algebra. So I'm going to move a square root 2 to the denominator. And we get 4 root 2 times pi epsilon 0. And then in these parentheses, I have half of an R squared plus another R squared. That's 3 halves R squared. And that's all raised to the 3 halves power. So if we take the square root of that R squared and then cube it, that gives us an R cubed in the denominator. And then we still have to simplify this 3 halves to the 3 halves power. Notice that one factor of R is going to cancel here, leaving us with R squared in the denominator. And then 3 to the 3 halves, that's the same as saying that we take the square root of 3 and then multiply it by itself 3 times. That's going to give us 3 square root of 3. Then the 2 to the 3 halves, that's going to end up in the numerator of our final expression here. And that's the same idea. You take the square root of 2 and then multiply it by itself 3 times. That's 2 square root of 2. A factor of 2 is going to cancel, leaving us with a 2 in the denominator. And a factor of square root 2 is going to cancel. Now the coefficients out in front of pi here, that's a 2 times 3 times root 3. So I can write that as 6 root 3. And then we have pi epsilon 0 R squared. And there's our maximum electric field on the axis of a uniformly charged ring. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.